Hello, I was playing around with the app that I had developed and I was looking at the flat earth map mode thing that I had developed. And I was thinking, is there another way that we can rule out the shape of the earth? And what I thought of was, what about the daylight hours? So, for example, right now on the 26th of March, I put myself at the equator at 90 degrees west. If I move the slider around for a 24-hour period, you'll see that the sun sets at 6:05 p.m. and then it's night, and then the sun is going to come up again the next morning at around 6:05 a.m. I was playing around with the days like this here, and I was kind of surprised not living at the equator. Throughout the year, at the equator, it always seems to be about 12 hours. But living at a latitude of 45 degrees, I know that the daylight hours change significantly between summer and winter. I already knew that there was a NOAA solar calculator. It's a spreadsheet that they have developed to calculate the daylight hours, the altitude and azimuth of the sun for any given time at any given location, along with sunrise and sunset times. And so I took that spreadsheet and I decided to create this tab. I removed a lot of the columns that were not necessary, and after a few slight modifications, I was interested in the sunlight duration column, and I picked three different dates: the December solstice, the March equinox, and the June solstice. And I also did the calculations for each of the latitudes from the North Pole to the South Pole, and then I made this graph. So the blue line represents the December solstice by latitude, and you can see that in December, the farther south you go, the more the daylight hours you have, and the farther north you go, the less daylight hours you have. On the equinox, it doesn't matter where you are, you're going to get about the same amount of sunshine. And in the June solstice, you get a curve that is a mirror image of the curve for December. I decided to look at it in a slightly different way again, and I thought, instead of calculating for every point of latitude on just a few days, what if I were to use a few locations and plot it for every day of the year? And so that's what I did here. So now I've got the daylight hours at the equinox, I've got the daylight hours at 45 degrees south, and I've got the daylight hours at 45 degrees north. Once again, as you can see, the north and the south are mirror images of each other. But when I look at what the AE map should provide, in terms of daylight hours, I intuitively feel like there's something that doesn't quite fit, that if the Earth truly was flat, that should not be the case. So what I did initially was I generated a bunch of images at very key points: 45 degrees north, 45 degrees south, December solstice, spring equinox, June solstice. Then I loaded each of them in GIMP like this, and I just used the measure tool to measure the distance between the sun and the observer, either at sunrise or at sunset like this. And I created this. There are the three basic events: 45 north, 45 south. These are the distances in pixels that my program I wrote exported. And then I took the average between sunrise and sunset to get an average pixel for both. These are just copies of these cells, and this grouping here is what I'm using to make this graph. I then also used the sunlight duration calculation for the 45 degrees north and the 45 degrees south over here, and then I made this chart here. So the red line is 45 degrees south, and it slopes down from December to June, as does the daylight hours slope down. So that looks like it could correlate more or less. However, when I look at the 45 degrees north, 45 degrees north actually slopes down when the daylight hours slope up. At this point, I went back and I grabbed another copy of the full NOAA Sun calculator, and this is the NOAA calculation plus, because the plus are a bunch of extra columns that I've added here. So these are columns that I've added, and from here on to here are columns that I've added. So Flat Earth Distances version 2, what I did was, instead of using pixels, I went and I calculated the flat Earth distance in kilometers, which you can see I'm doing from the math here. And by the way, I'm going to make a copy of this spreadsheet available, so check the description below. So given that I can calculate the ground position of the sun, or the subsolar point, for any location at any time, and that I could ostensibly calculate the distance between my location and the subsolar point, if the Earth was flat, I could then turn around and calculate the flat Earth distance. And so that's what I did here. I started with December 21st of 2021, and for 45 degrees north, I made a copy of the distance at sunrise and at sunset, and then I did the same thing for the distance from the observer to the subsolar point for sunrise and for sunset as well. I did that for December 21st, January 21st, all the way to November 21st of 2022. I averaged the distance to the subsolar point at sunrise and at sunset, and that becomes the distance at 45 degrees north. I do the same thing again for 45 degrees south, and I also copied the daylight hours expressed in minutes. I used this to be able to specify the vertical axis range, because otherwise it would want to start at 0. And so what does this tell me now? At 45 degrees south, the distance to the subsolar point of the sun is almost 24,000 kilometers, and then reduces to just under 14,000 kilometers, and then goes back up again. And that mirrors the daylight minutes. When I look at the northern hemisphere, 45 degrees north, the pattern is completely opposite. The distance between the observer and the subsolar point at sunrise and at sunset gets closer at June, just like it gets closer at 45 degrees south. However, in this case, for the north, the daylight hours increase rather than decrease. Here you can see that the daylight hours are mirror opposite of each other, but the distance to the subsolar point is not. So the last thing that I decided to do was to implement the Haversine formula to calculate the distance to the subsolar point from the observer at sunrise or at sunset or at any given time. And that is this column here, just copied over so I don't have to keep scrolling all over the place. So I took this column and I created this tab. And as you can see, in this case, 45 degrees north or 45 degrees south in the entire year range, the minimum maximum distance is only about 50 kilometers, which is more due to the fact that I grabbed the one that was closest to sunrise and closest to sunset when the NOAA spreadsheet was dealing with time every 6 minutes. If I were to go to find the exact second that the sun rose above horizontal eye level, all of these would probably be very close to each other, probably within 1 kilometer. When I was working on the spreadsheet and creating all of these various tabs, there was one fundamental issue that I thought of, and I just about forgot to put it in this video. How do flat earthers explain the sun setting if the earth is flat? Flat earth geometry and perspective demands that the sun cannot have an angular elevation of any less than about 9 or 10 degrees. That is, if you're standing at the South Pole looking towards the north and the sun is on the other side of the earth. For most people on this planet, the sun should never appear below 16 or 17 degrees, even at midnight. And yet we can see every day that the sun appears to go below horizontal eye level. Flat earthers give excuses like atmospheric lensing. Some will say that it is due to the humidity in the atmosphere or microscopic air droplets or something like that. But that would necessitate an inconsistency in daylight hours. In other words, if it was due to atmospheric conditions, you would have sunrise at 6:30 one day and 6:27 the next day and 6:40 the day after that. If it's based strictly on distance, like I've shown here, the daylight hours between one latitude north and the same latitude south would not be a mirror copy of each other. So this is an exercise to flat earthers who keep saying, do your own research. Well, I'm going to challenge you to do your own research and to think about what is the real mechanism behind why the daylight hours, for all intents and purposes, appear to be impossible if the Earth was flat as you claim that it is. So there you have it. I think this is yet another way that we can determine whether the shape of the Earth is a globe or whether it is flat. And as you can see, this is still more evidence that the Earth is a globe rather than being flat, like flat earthers would like us to believe. And all you would need to verify that would be a stopwatch, a piece of paper, a pen or pencil, and a desire to visit different locations of the Earth and to make observations everywhere you go. That's going to be it for this video. Thank you for watching. If you liked it, I would appreciate the thumbs up, the subscribe, the comment below, and all of that other good stuff. And I'm going to see you again in another video soon enough. So bye for now.